sum of the measure of equal. So this was just because we had that for finitely many, if you remember. Then somebody will ask for infinitely many, because there was a proof where we had to prove that the countable union of the sets of measurable set is measurable, if you remember. So we use the finite, that this property holds for finitely many when it is intersected with any set. So here let's prove this guy. So essentially it's just again the passage to the limit, because we have that for finitely many. Okay. The statement is true. It was a previous proposition. That was that M star A intersection, the finite union, is equal to the sum over K of M star A intersection. Now, if you remember, this is what we proved. Okay, so we have that the M of the union of EK, just take A to be the R, with sum up to N measure of EK. So, I know that in the morning it's always difficult to start with something like that. So, how to pass the limit?
The right hand side is bounded by the summation to.
Well, that one.
The right hand side.
Yeah. But you don't know if this is plus infinity. Basically, there is nothing to prove clearly, but actually, so.
Summation we extend up to infinity. We extend up to the union up to infinity, and by summation
Monotonicity.
monotonicity.
So passing to the limit, this is larger than the sum, but we know being an outer measure that is low. So then pass to the limit. In N. So let's see. So now we have this guy. I really want to write this. But the blackboard here is a little bit claustrophobic, I have to tell you. For mathematicians, it's claustrophobic. So here we have the sum. And passing to the limit, we get the M of the union and the other, and then okay. Because the other is for the other measure. So this is sufficient, no? So I don't have space, otherwise I would have written the sentence. So M now is really a measure, so the corollary, just take definitely M is a measure. Which means that M, now let's say this guy, and M is sigma additive. So we conclude finally with all the construction of the Lebesgue measure.
Hallelujah.
Huh?
Hallelujah.
Hallelujah, yes. Well, 2 hours and, no, 3 hours actually. Okay, so let's go on with some, as I told you, some theorems that allows you to pass to the limit. Well, this statement is the first passage to the limit, no? Because the limit is over here. So the value of a set is the sum, the limit of the partial sum of the pieces. And if you remember, this is basically what we expect to be the length, the measure of an open sector, the sum of all segments. So theorem, so two parts. If EK is a sequence of measurable sets, and EK is is an increasing sequence converging to certain set E. So it means that this notation is that EK is contained in EK plus 1, and essentially the E is the union of EK. No? Then the measure of E is the limit of K of the measure of K. And the second, if EK L and EK now decreases to E, so it's the opposite, is contained in EK, and E is the intersection, sorry, of K of K. And the measure of E1, the first one, is less than plus infinity, then the measure of E is again the limit over K, the measure of K. What is very nice because we don't need to care about the structure of sets, no? It's really... Okay, proof of part 1. We have the corollary, so the previous proposition, so it's...
Can decompose E sub K to...
Yes, and then the limit becomes the limit of the series, no? So E is equal to the union over K, EK plus 1 minus EK. Okay, I should not finish because now we have that the measure of K is the sum. So the measure of K is the sum up to K minus 1, the measure of, let's say, so yes, let's say these are the set Fk and Fj. That's it. So the limit of the series becomes now the limit of the set. Okay, second part. Is it clear for anybody? So, are you able to reproduce the proof without looking at the blackboard? Just a tricky question. Point 2. So there is a problem in point 2. What is in the sentence something which tells you that you need to think a little bit?
Because we require the measure to be less than
Yeah.
refined.
Okay, so now to complete the thing is that, okay, we need to use this and show that if this assumption is not valid, then we have a counter example. So it's really neat. So what do you do?
We use complements and
You do the complementation, yes.
Complementation.
Yeah, because now you use, so that now Fk is equal to E1 minus Ek. So now we know that the measure of the union of Fk is equal to the limit of the measure of fk. And now this guy is equal to the limit of the measure, well, by the definition, is E1 minus the measure of Ek. And this guy is again the measure of E1 minus the measure of E. Because the union is, the complement of the union is exactly E1 minus E. Okay, so you see that is needed, otherwise I have plus infinity and there is no this cancellation property. And then and E1, well, E1 means one of the sets. Less than plus infinity needed. Why?
To cancel. To cancel. Why?
Cancel, yes, but maybe there is another proof.
The measure of fk is not plus infinity
We can consider
because of we need to this
The measure of what?
fk
Is not plus infinity, yes. But if I remove this quantity, why?
Yes.
Why? No. The measure of 0 plus infinity is plus infinity. The measure of the complement is minus infinity, 0 still plus infinity. Because
we can consider
it's not a group with plus infinity.
we can consider interval n to infinity.
Yeah.
And the intersection is equal to pi. It was measure 0 when but
Okay, so the intersection of, what is the intersection of these sets?
And
Is the empty set, and the measure actually is always plus infinity. So 0 cannot be done. Okay. So just a digression here. I'm sorry. I know that it's difficult maybe for people that don't, but the previous proposition, these two theorems, is the base of everything. So the fact that you can pass to the limit in some, let's say, with a lot of freedom, no? You see. So the only thing always you control is that you don't get this plus infinity you don't have to cancel plus infinity or divide by 0. Okay, now let's go a little bit with another notation, which is the following. And this is very common and is why the measure theory is very useful. A property P is said to hold on A if there exists a set N with the measure of N equal to 0, such that it's to hold, I forgot, Lebesgue almost everywhere on A, such that P holds for all x, so these are property of a point, of points, for all x in A minus N. So essentially I say a property holds almost everywhere if removing a set of measure 0, it is valid pointwise. For example, I could say a function is almost everywhere continuous. You remove a set of measure 0 and in all the other points the function is continuous. Okay? Sets of measure 0 are very bad, however. So it can be dense, uncountable, and dense. So now a digression about this statement. So very often you have to prove something, and you have a measure on the set, so it's very easy to prove that this holds removing a set of measure 0 which is constructed explicitly. So the answer is good in the following sense. Suppose this measure is something like the probability of having an event. So it means I'm sure that the event will happen, will satisfy my property. Because I remove a set of measure 0 which probability is 0. So the answer is sharp. What is missing is the fact that to say which is the set n is difficult. So you construct n and you prove as measure 0 by saying I remove the sets where, for example, I don't know, if I want to prove continuity, I say, well, the set where the two limits are larger than epsilon. Okay. And this is a set which is well defined, and maybe you can prove as a small measure because of other properties. But it usually it's difficult to say which are the points. So this is something, in my opinion, is the strength and the weakness of measure theory at the same time. So you can answer a lot of questions by removing a set of measure 0, but which set you remove is very complicated and difficult to write explicitly. Actually, usually you don't write it explicitly. So this is just so for example, this is the following lemma. Assume that Ek is a sequence of measurable sets such that the measure of the sum of the measure of Ek is less than plus infinity. Then f of x, which is equal to the number of k such that x is in Ek, is less than plus infinity. Okay, Lebesgue. Okay, I'm sorry, this is my mistake. This is n. And now I can explain also why the mistake, because usually I stick with the book that it calls the Lebesgue measure m, but in the literature and the why, usually when I write papers I use L for the Lebesgue. And so the Lebesgue value is always L, but actually the measure is also called L. I'm sorry. This is the correct one. So for any given a measure, remove a set of measures 0 with respect to the measure. Okay, so this property. And now, so the proof. Any idea? It seems
what is a property? Yes.
Finite. What is a finite?
property is that for any x, I now compute the number of point of a k index such that x is in the set. Then the property is that this quantity is less than plus infinity, so it's finite. Removing a set of measures 0. Okay, so let's construct well, if you don't look at the proof, well, it is dependent on what you want to do. So let me say, so the set which are in E1, so I put E1 like this one. So this function is the sum, so function is the sum over k of the indicator function of k evaluated at x. Do you
Sorry,
agree?
I don't understand the set in question.
The?
What do you want to prove?
Okay, so give me x, and then you can find a set of indexes such that x is in AK.
For every k?
Yeah, I mean, not for every, therefore
Oh,
take
okay.
k,
Okay.
if it is inside the k, is inside the set, otherwise it is not. So now you count how many.
So that's the number of sets that contains X. No?
That-
The
that's-
number of EK that contains X, no?
It contains, yes.
Yes. So it has to be fine.
It has to be. Well, let's see.
That's what we want to show.
It is?
We want to show that it's finite. There is finite number of EKs that contain.
For almost, yes, but for almost, so if you fix x and then it is finite if you remove a set of measures, otherwise it is not. Let's do this.
If these sets are infinite and if you assume the contradiction that the set is not of measure 0, then there would be a set of finite measure inside every set. So their sum would be infinite.
Yes. You understand the proof? So I was going to do it graphically and just observing this thing here, no? F of x is the sum of the indicator function. But actually your proof is not correct. Because you know that there is an infinitely many, so you know what? You say that if it is the number of such a
I'll take the intersection in some way. I'll take each, I'll have the indices intersect in some way. But roughly.
But you know that you can partition the set n. So you are doing a partition of the set n, and you are pretending that there exists a so for any x, so assume this holds for any x. So for any x, then this number is plus infinity, which is a subset of n.
Okay.
Take a different x, you have another subset of n. And why their intersection cannot be finite? Which means that or that it can be 0, because you know that you have a lot of space. So it's close, but there is this trick, no? I mean, the idea is correct, but is there is this intersection which makes you trouble. You cannot say that the same set is under all the others. Okay, but this is true. That by definition, the value of f is exactly the sum of this function, because this function is 0 when it is outside and 1 when it is inside. So let's do the drawing now. So let's say this is 1, then I take E2. If this would be E2 is equal to, put E2 here, no? So this is E1 intersection E2, and this is E2 minus E1. And the function is exactly that function. Okay, so essentially, I can go on. Let's say I have a function which becomes very complicated. In this case, I'm clearly missing what is the value of ek. I just keep the function f. This is the only information. So let's go back. Which property? So what is now f of x for fixed x? So it is this length. So let's compute what is the integral of f of x. I know that is not yet defined, but I want to understand. Then we do another proof. But just to have the feeling. So what is the integral of f of x? So is this RA? So what is this area?
Some of the measurables.
Less than plus infinity. And now, if f of x is plus infinity on a set of positive measures, then this is plus infinity. Because if I have, for example, on this, let's say interval, this is plus infinity, clearly the integral of f is this area, and then I get plus infinity. So this is not a proof, it's just, well, it's not a proof until you don't have the notional integral that will come in But if you keep the notion of the area, it is the proof is this. So essentially, you have a function which has bounded integral. It cannot be plus infinity on a set of positive measures. It can only be finite. Because otherwise, the area is plus infinity. Now we do the real proof. So define A, K are all the x such that, that x belongs to the union from k plus 1 to plus infinity of ek.
Take the intersection.
So essentially, if you go back to my picture, is the fact that now I define this AK, essentially something like taking the level set of this function. And now your works if EK is a decreasing sequence. And this is the decreasing sequence. So just, well, everybody has to interpret the things. So the proof is just a sequence of logical steps. But then the interpretation is up to the single person, in my opinion. So we are not, we don't write in machine language. So okay, then EK is decreasing to a set. Let me call already n, such that what is the measure of n? Okay, this is finite. I can apply the previous theorem. Is the limit of the measure of EK, and the measure of EK is less than the sum from k plus 1 to n to plus infinity of the measure of, this is AK, this is EK, and this thing is 0. Okay, so now for any x, for all x not belonging to n, there exists k such that x does not belong to EK, because otherwise belongs to the intersection. And then f on x is less or equal than k. Because it does not belong to EK, at most intersect the first k EK. Okay, so the very nice theorem, as I told you, what is n? Well, it's a little bit difficult to build, no? Okay, yes, the intersection of this union, so you have already to do a countable union, and then take a countable intersection. Okay, so let's do some exercise here. Actually, did you solve the exercise yesterday? Too early. So E1, E2 are measurable, then the measure of E1 union E2 plus the measure E1 intersection E2 is equal to the measure E1 plus the measure of E2. Okay, well, this is that's 0. Now what we have proved that for all A in the power set of R, the outer and EK contained in the Lebesgue set is joint. Well, what we expect, then the outer measure of the partition is equal to the sum of the outer measure of each part. Now it's the extension of the previous proposition up to plus infinity. Okay. So now there are still two parts to conclude the Lebesgue measure, is that we are going to construct some bad sets. So a good measure, a set which is measurable, very complicated, and a set which cannot be measurable. So the book follows, it gives some general condition, but my feeling is that you understand the construction with a specific example, and then the rest is, you only repeat this construction. So the construction is the following. So consider 0, 1, and let x is equivalent to y if x minus y belongs to Q. For x, y, and 0, 1. So this is an equivalent relation, no? Any doubt about it? Just a go. Very well. So let x plus q in the section 0, 1 is the equivalent class of x. And now what I can take, I can, okay. Let me ask you if I take a, what is called a section. For all Ex, there exists a unique, let's say, x bar. Let's say, well, I call it y of x, actually it would be the same x, which is equal to a x intersection A. So A is a set which has exactly one point in each equivalent class. Can I do that?
I need the axiom of choice, please.
I need the axiom of choice. Otherwise, I cannot build it. So, really, this is the, well, one of the equivalent formulation. Okay. So now I wonder if A is measurable or not. So let's say some remarks about A. A plus Q in intersection A is equal to the empty set. Actually, this notation is wrong, sorry. It cannot be like this. Because otherwise I'm taking, well, you understand what I mean, but formally it's wrong. This is correct. For all Q in Q. Is that okay for you? But why? Well, it can be okay, but why?
Because
This
You take use one.
Yeah, because in the if there is another point, then so okay. Is partition
so it should read in Q star.
By
Q star.
what is Q star?
And the rational is minus 0.
Oh yeah, sorry. Yes. This partition into n equivalent classes. N, let's say, sets, which is A intersection, so Q plus A intersection 0, 1. It's okay for you? So Q, let's say Qn, and Qn is an enumeration of Q. It is okay for you?
Into n set.
What is A?
Ah, yeah, sorry. A countable number of sets. We mean countable many sets. So it's okay?
Yes.
By translation, let me see if I have to add something. No, invariance of n or m star. Let's say that m star of A plus Q is equal to m star of A. But this is the translation invariant. Okay.
The previous statement I don't understand. Q is equal to the last.
So Q,
Yeah.
take an enumeration of the rational numbers.
It's a union or?
Is a countable in many rational numbers. So you can take an enumeration because they are like, is a subset of n times n.
Yeah, okay. It's a countable.
Countable family of
Right.
rational numbers.
Okay.
And now we take the translation of A and, okay, here I'm a little bit sloppy, I should extend modulus 1, I should always say, no? Because if I take plus Q and A is just inside, I have to subtract 1 in order to come back. So let's say this is the translation modulus 1. And this is modulus 1. So when I translate, if I go out the interval, I just come back. But modulus 1 being a rational, I'm not exiting by to the, I mean, the fact that the intersection is empty also modulus 1. Okay. So, and now this holds also modulus 1, no? So if I take a set, I translate, I cut the piece, I put it back. Essentially, I'm intersecting with a measurable set. So what I do, I construct countable a partition of 0, 1 into countably many sets which have the same measure.
So measure of interval is infinite.
Or this guy has measure 0.
But
Yes.
the interval
But then
has
it's a contradiction.
So it's not measured.
Okay, so this is basically the trick, and then all the rest is done by just, so let's conclude. Then, hence, if A is measurable, 1, which is the measure of 0, 1, should be n times, so plus infinity, so let's say it should be the sum over n of the measure of A, which is impossible. So this is a contradiction. Now, now the general construction follows the same route, with the only difference that, well, clearly what you can do is if you have a measurable set, non-measurable set, and then you transform it in, for example, in some controlled way, you get a non-measurable set. So, general case. So, use the previous construction. And transform it in some way, in some controlled way. Okay, so let's see another example, how to do, instead of having the ratio, maybe something else. So I cancel, and then we do another example. And the construction you will see is always the same. In 0, 1. So 0, 1 means a set of positive measures. Because in set of measure 0, all subsets are Lebesgue measures. Define x is equivalent to y if x is equal to y plus n, sorry, instead of n, let's say z alpha, with z is in the natural integers, in the integers number, and alpha is in minus q. So it's like the previous one. Instead of having q, I have still counter-many points. So essentially, if I have x, well, there is a way of seeing it, which is the following. I say that, let's say I say plus alpha. So this is the identity. And then I add alpha. So if I start from x, the next set is this one, x plus alpha. X plus 2 alpha, and then I go on. No? You see that what I'm doing is that I'm essentially following this discrete dynamical system. This is an orbit of this discrete dynamical system. Okay, so next step. If you look at the construction, the next step is to find the section.
We choose a point from each set and take the unit.
So if, let's say it is equivalence of x, a intersection x is equal to some, let's say, whatever, point y, which depends on the class. In any case, is unique. Now, what would be the transformation with let alpha to have the same measure, but the intersection with this translation or is 0? Okay, just look at the class. So the class is x plus z alpha. So it's a plus z alpha intersection a is equal to empty for all z. Now I remember minus 0. That's it. A cannot be measurable because, well, the measure is the same, just the translation, and then, okay, modulus 1, this is modulus 1. Then I come back. So A cannot be measured. So you see, it's always, the trick is always the same.
Are there non-measurables? Are there non-measurables
Well, yes, but at the end, the problem is always to build one. So, yeah, certainly there are.
But are there examples?
Usually the example that I know I think because there is a general theorem which says that up to some transformation you get this example, I believe. So up to a Borel transformation of the set, you always become one of these two. Well, this example is given to the other.
So
you always
it's basically this example.
Basically, there is always this example. I'm not so sure this is true in the case of, let me think. Well, the problem is always that everything here, now we fix the set, 0, 1, but you can take a general set. And and if you have a non-measurable set and you have a Borel transformation, which is an invertible Borel transformation, whose inverse is still Borel, then the measurability passes, and so no measurability passes. So at the end, you can squeeze, transform 0, 1, transform the set, and then still remain non-measurable. So I would say, but the proof of this statement requires something like up to the equivalent classes of measurable spaces. So they are equivalent because this happens. So I should say that, yes, this is basically the examples.
Excuse me, I think we need to take a fractional part of the alpha or no? Alpha is irrational.
Modulus 1. Yeah.
Okay, it's fractional.
Sorry, I forgot. Yes. When you go farther here, so when you are here, you re-enter on this side. And it is that this one is continued here. So when you arrive here, actually you go down here, and then you re-enter on this side. Yeah, that's the metric system. Okay, so this is okay.
I'm sorry, what's model 1?
Modulus 1 is what is at the fractional part. So is modulus the integers, only the what is after the comma, after the dot. What is here? Okay, we already jumped to another section, and here is okay. Now we go on with a second stage function and set. This time they will be measured. And then we merge the two things to prove that essentially you have subsets which are very measurable but not Borel. Here the notation is a little bit strange because usually is the Vitali staircase is a function, the David staircase is a function, or the Vitali function, or the Cantor set, that's standard. But the book called Cantor Vitali function, so as I should say that Cantor set is the true notation and Vitali function is the other one. So we are going to construct something which is a fractal set, and the function which is constant outside that fractal set. And so the trick to construct fractal sets is always to use a transformation that you rescale with some fixed rules, and then pass to the limit, and prove that the limit exists in some space. So let's see the proof. So the transformation is the following. Assume that the function is defined from A, B, with values from integer rectangle. Well, I don't care. Then the transformation T, which should be indexed by A, B, and this function, this interval, but I don't want to keep the notation, I want to keep the notation light, is I replace the function inside this rectangle by just, I divide it set by 1/3. So this is A, 2A plus B third, A plus 2B third, and B. I take the middle value, so let's say this is y1, y2, y1, y1 plus y2 half y2, and I do the following. This constant in the middle 1/3, and then is linear here and linear there. So if you give me a function which, well, I can even assume it's outside, but it will not be applied to that case. I replace this part of the function which a fixed graph. So this is the transformation which will build the fractal, or the function. So now,
I'm sorry, where did the function go?
the function, okay, here you have a given function, you just take one interval, which you decide which one, and then replace with your given prototype.
So it seems like this doesn't depend on the functions previous one.
No. This will be applied to our function, so we will see what to do. But
So if we have two different functions, will they produce the same?
Yeah.
Okay.
I don't want to confuse about this point, because it will be applied to a specific function. But it's just to say that you have to define a transformation. Here I prefer to define the transformation on the larger domain I want. At the end, will be applied to recursively only to these parts. So I should say this is applied only to functions which are affine inside one interval. And then I restrict the domain, but since I'm using, I can enlarge the domain as much as I want. I don't want to confuse you about this point. Otherwise, if you prefer, we can just say that this is applied when the function is linear over here. It becomes like that. So now I give you the procedure. And it's the way that you choose how to apply the transformation. Transformation depends on the values here. Okay, so step 0, you start with the identity. You don't care what is outside. And now, step 1, you apply the transformation to the whole set. So it becomes 1/3, 2/3, 1, 1. The value here is 1/2. Okay, I don't need to write. Step 3, step 2. What is the new graph? I apply the transformation inside here, so the 1/3 is left, constant. I divide it by 1/3, so it is 1/9, 1/2, 1919 length, so 0, 2, 9, sorry, 0, 1, 9, 2, 9, 1/3. So this is will be 1/9, 2/9, 1/3, 2/3, and this is 7/9, 8, 9, 1. And now the value here is 1/2. The new value is the middle value, so 1/4. And the new value here is 3/4. Okay, next step. I apply again inside all of these pieces, no? Very well. So at the end, we get something which is so you see why it's called the David's staircase. So let's see now. So this is graphical. Now we do the computation. So for example, first of all, I want to know if the function is converging, because maybe I need something that goes to infinity or does not converge, so it's empty. Keep in mind a little bit procedure. So let's compute what is the distance Fn minus Fn minus 1 in norm C0. You know what is this norm? It's the supremum of the maximum of the difference in values. Okay, so let's see. So every time, so let's compute. What is the size of the perturbation I'm applying at each step? Start. Step 1 is 1. And the distance is bounded by, well, most would be, I can also call this guy 1/2. It's even better. I say 1/2. So here now we're applying to a size which is 1/4. And the distance is 1/8 at most. The next step will become 1/8. So what is now the perturbation? So at each step I'm applying transformation to a set whose 8 is 2 to the minus I, so 2 to the minus n. So the size is almost 2 to the minus n minus 1. Minus n plus 1. Here I have the minus 1. And what is now the length of the set to which I'm applying the transformation? Well, it's the opposite of what I have here. So it's 1/3. So the area where, let's say, Fn is definitely constant. So it's not constant with n, with respect to n. So it's 1/3 at the step 1. Then I have 2/9 at the step 2. And then, okay, the last one will be 1/3 times 2/3 to the power n minus 1. I'm just iterating. Because every time I add 2 to the n segments of length 1 to the 3n. So each time I have 2 to the n pieces of length 1/3 to the n. And then I'm removing 1/3 of the remaining set. So it's a zigzag. Okay, so this quantity is, well, we don't need to compute. But okay, it's, what I can do is 1/3, 1 minus 2/3 to the n plus n divided 1/3. So it's like this. Very well. Okay, let's use the two parts. So first, This implies that Fn converges uniformly to a function phi which is continuous. And the I hat increasing. Simply because Fn is increasing, no? So it's monotone increasing. And now let me observe that so once Fn is constant, it's not only constant with respect to n, it's really constant in each of these intervals, no? So Fn is constant, so then the limit is constant, so phi is constant in each of the intervals. Okay. Whose length is this one? I should write the formula. Let's say ik and such that the measure of the union of ik is equal to 1. Okay, so now you understand why it's called the David staircase.
Code A?
Hmm?
What is it called?
The David staircase. So essentially, it's a function which is so it's a continuous function which is constant on a set of measure 1. Nevertheless, the two endpoints, one is value 0 and one is value 1. So essentially the steps are infinitesimal, but how many do you have? Uncountably many. So we have this function. That's what we do with this function. What the route I want to do. Okay.
Why the intervals, number of intervals are uncountable?
The intervals are countable. Is the complement of the intervals.
Yes.
So 0, 1. So this is we have to check it. So what we want to prove is that zero, 1 minus the union of this ik is uncountable, compact, and with n interior. As all the properties that you can expect, it's perfect, which means it coincides with its limit points. And I'll say the measure of k is equal to 0. So it's a very strange set, no? So here is a set that you cannot draw it, but you can imagine that removing all these open intervals, what is left is something on measure 0, but still as a cardinality of R. Okay, let's see what. I'm not following the notes now, but I have to do it.
So, is this the Cantor-Vitali function or the Cantor-Vitali?
Cantor set.
Cantor set is k, and this is the Cantor-Vitali.
I think this is the Cantor-Vitali.
Hmm?
This is called Vitali or Vitali function.
This is count of set. Is the famous 1/3 because 1/3 is the 1/3 over here. And this is actually in the book it's written Cantor Vitali. My notation will be the Vitali function. Okay, so let's add something. So now we have the function, we can cancel this guy. And so, first step, let f equal to phi plus the identity, plus x. So, it should be f of x, phi of x plus x. Phi is strictly increasing. Do we agree? Clearly, because if phi, f is strictly increasing, phi is increasing, x is strictly increasing. Okay, so continuous. So f to the minus 1 is increasing, strictly increasing and continuous. Here we have this trouble interpoints 1/2, but f of the union of intervals, so the measure is equal to 1. I'm doing with some properties. So now you imagine that now the function is tilted, well, or is stretched upside by sides. 1, here everything becomes, so now the function goes up, this one becomes segment, this becomes another segment, and then at the end I go to 1. Do you agree with this? Yeah, this is a countable union of image of intervals, because being strictly increasing continuous, I have that this is the union of the images, and inside this guy, phi is constant, but x is the identity. So it is a sum of segments which are exactly the same. It's something like I'm stretching here.
UI is the partition of 0, 1. UI is the union of 0, 1
This exactly this set over here. So let's say this is U1.
Yeah, this is the partition of 0, 1.
No, it's not a partition.
I mean it's a union
Because
of
k plus the union of this one is 0, 1. I still have k.
okay.
Now f0 equal to 0, f1 equal to 2, which implies that the measure of f of k is equal to 1.
F of 1
Equal to 2. Because this is 1 and this is 1. So the measure of f of k is equal to 1. So to which one now I'm answering here? Well, compact is easy. Empty interior, it's easy because it has measure 0. Compact is from here. Empty interior, the measure of k is equal to 0, which is from here again. We will see that it's perfect. And so it's here.
So
now, which one I'm answering? Which is
so
also
it's of measure 1 and every countable set is of measure 0. So every countable set is of measure 0.
Yeah.
So this has to be uncountable.
Yes. Because if it's countable, the image of a countable set, the function, remember, is 1 to 1, is still countable. And then it turns out that, well, it cannot be countable. So this one I'm answering to this question. I have a continuous function which maps 101 the set to a set of positive measurements. Cannot be measured or countable set. It's strange, no? Because why it's strange? Because what is the union of the closure of the intervals?
Union of the closure.
Of the intervals I1, I2. So how many points I add to get the closure of the intervals? Can't be made. So it's not contained in the boundary points of the intervals. It's much larger set. So now we have the thing. Now let's see what we want to okay, now we use this function f to build a set which is measurable with respect to Lebesgue, but not Borel set. Okay, so f is given, and then I can answer here. Let's do the following lemma. If f is continuous, and then E is Borel, then f to the minus 1 of E is Borel. This is a very important statement actually. Okay, let's prove it. So essentially, I know it is continuous. So first step, open f to the minus 1 of O is open. And now, okay, I put the pieces. F to the minus 1 of the intersection of some sets is equal to
The intersection.
the intersection. But this holds also not for counter remaining, but we don't need it. And then,
The pre-image of everything.
yes. And then, okay, f to the minus 1 of the complement is the complement. Okay, and here I can take the union, no? In intersection or union, doesn't matter. Okay? Then, so this says that f to the minus 1 of a sigma algebra is a sigma algebra. And now I know that the f to the minus 1 of the Borel sets is a sigma algebra, and since it is continuous, it contains the open set. So the sigma algebra contains the open set, so it is clearly containing the Borel sigma algebra. So now the thing, you see, so this is completely general, and the continuity enters only here. Okay. So now the last point is this, how to use this theorem to prove that something cannot be Borel.
Sorry, you said.
How to show this?
You said.
How to show this? It contains a Borel. How do you show it's equal?
Um, yeah, because I'm going that this is, yeah, it's a sigma algebra containing the open sets. Because I,
It's
what,
also for closures.
hmm?
It's also for closures. It continues also will back.
Yeah, if we take that it's continuous on the other side, then
Also will back.
so it's continuous and invertible.
Wait.
Then okay, you have that the Borel set is something that it maps into.
Why do you need invertible?
No, in order to be sure that the smallest sigma algebra in the n space is the largest one. But I'm sure that this is holds, and now I don't see the direct proof. The only proof that I would do here is to show that since I construct the Borel sigma algebra by counting intersection and union, and I have that I can pass the operation outside, I start with the open and then I build I build the same sigma algebra. So if you give me a Borel set, then the Borel set is the intersection and union counted many times of open sets, and then from this operation I can pass all the thing on the other side, on outside, and get that it is a Borel set. Otherwise, let me see. But I'm sure there should be an easy proof about it. Okay, I'm thinking. Sorry, I need to think. Now I cannot see an easy proof. But the theorem is true. F to the minus 1 is Borel. Okay, because I need to finish. And then I will answer you. So let's give for granted. Okay, so now take a non-measurable subset of 0, 1. As before. Okay? So now what we want to do is the following. So let's do the picture. We have this strange set K, the Cantor set, which is mapped into a compact set of measure 1. Let me think, for some reason, I'm not following the notes, so now I'm really writing what I feel the theory. I would use something else now because so I would use the following. So I would use something immediately the function phi. So I have the function phi 1 to 1, and I know that phi of k is equal to 0, 1. Because it is k, okay, is a compact, so phi of k is compact, and phi of the union of intervals is contained, well, actually is equal to this set. So it's 1/2, 1/4, and then 1/4, 1/8. So by my construction, this is the form k 2 to the minus I, from I equal to 1 to equal to 0 to k minus 1. And then is the union over I. So these are the only values where the function is constant. The rest of the values are assumed by the values in k. And since this is a countable set, and this is compact, its closure is the whole interval 0, 1. Okay? So let A minus, let's say this countable set here, let's call it n, minus n. Is this measurable? A is non-measurable. Is this measurable? No, because if it is measurable, then A is the union of a measurable set plus set of measure 0, which is measurable. So this is not in L. And now, let B is phi to the minus 1 of A. Since I read of A minus n, since I remove n, which is the only point where it's constant, this is a set which is contained in K. I think in the notes I instead use the function f. I don't, but now for some reason I cannot get it. I follow another route. Is that okay for you? Okay, the question is B measurable? Is B Borel? Okay, the first one, is B measurable? Well, it's a subset of K. K is measure 0. So it is measured, yes. Because m star of B is equal to 0. Is B Borel?
Yes, B.
I need to use the lemma.
No, because of the lemma.
Okay, if B is Borel,
The image.
the image should be a Borel set. Here I'm using the fact that I should use F here in order to avoid these intervals here. But this is a contradiction because it's not even in L. Contradicting BA minus N is not in L. And and this answers a little bit your question, how to build non-measurable sets. It's always this way. So you start with a set and it typically is A. But I really think this is a general, there is a general theory that up to some in equivalent classes, this is the only construction. But I'm not sure, I have to check. And then you take a Borel function. And then it turns out that any image of a non-measurable set or counter image cannot be, well, if the function is 1 by 1, cannot be a Borel set. And so cannot be measurable if with the right measure. Okay? So I think that's it. Let's see, there is an interesting exercise which is the following. assume that f is continuous. If E is Lebesgue measurable, does this implies that f to the minus 1 of E is measurable? Well, this is exactly what we use here. No. Set of measure 0 can become something, well, as bad as you want. Because there are continuous functions which maps set of measure 0 into set of positive measure. Assume that f is one Lipschitz, which means that f of x, f of y is less or equal than, well, x minus y. Then E belonging to L implies f to the minus 1 of E, or let's say f of E, let's say, and Lipschitz and strict integration. In order to avoid the problem. Now, does this implies that this hold? And now the set of measure 0 are mapped into set of measure 0 because of this estimate. So it's true. Construct a Cantor set using the same procedure and removing A 1/3 with A less than 1 at each step. So the picture, instead of removing 1/3, I remove A third, then I remove here, this is A third times what is left, which is 1 minus A third divided by 2. And then I go on, no? I think this is not going. No, this is I divided the A third square here. No, because otherwise it becomes A. So the procedure is that at each time I divided A third to the I. Yeah, because otherwise I get. So prove that the limit set is compact, empty interior, but less positive Lebesgue measure. Okay, it's a little bit strange, but actually you have this ghost in the real numbers. So deduce that the measure that in general, the measure of the closure of a set minus the interior, so the boundary, this is the boundary, is greater than 0. It's because this is the boundary of the open set you remove is exactly your Cantor set.
Interior.
Hmm?
Interior symbol dot is interior.
Yes, this is the interior.
Just the middle boundary.
Yeah, yeah. Here in the interior is that itself. This is the opener.
What is the limit set? What do you mean?
What?
Prove that.
The limit set is compact. Let's call it this K. No, again, K is is what is left when you subtract all these intervals. Something else, but it's not. I'm already out of time. Okay, so this is another fundamental thing that you can build, and together with the non-measurable. The non-measurable is actually something strange. You need the axiom of choice, but instead the Vitali staircase. So a function which maps set of measure 0 into sets which are of arbitrary length. It's an important thing. And the other is that you have this compact set. Essentially, they don't have any interior, but they still have positive measure. Okay. So I think it should be right next Wednesday.